or 1000 decibels per kilometer, which means every 10 meters you go, the power falls by a factor 10. So at the end of 1 kilometer, your power will be 10 to the minus 100. Now if you know any doesn't matter what kind of science you are in, but 10 to the minus 100 is as close to zero practically as you can get. So even a kilometer later, there is no hope of doing any optical communication. That's the problem. And two key developments happen after this. One is the invention of the laser, and the other is Charles Kao. So first let's look at the laser. In 1960, the ruby laser is invented. Very soon after, Ali Jaman and company invented the neon laser, and in 1962, 4 groups invented the semiconductor laser. Now you have a bright light source that is available, which allows you to experiment. Earlier you were working with lamps and whatever else. Now you can work with a very bright light source, allows you to do experimental work, but even if the fibers are lost here, I can still work with them. And now I must take a little aside. We will come to Willard, Boyle in part 2. This guy is an amazingly versatile guy. He is listed as one of the inventors of the CW laser, and he also is on one of the patents for the first semiconductor. Very versatile guy. He's got his thing for the CCD, we'll have to wait for a while till we hear his story, but that's the laser. The other part is Mr. Kao. So Kao is a Chinese person. He's born in Shanghai. In his family, he moves to Hong Kong. He adopts a more Western name called Charles Kao and moves to the UK for undergrad studies. He studies electrical engineering, gets his BSc from London, and then he joins the company while working for his PhD. So his PhD is kind of an on-the-job kind of thing. And there is one group which is still toying with the idea of optical waveguide communications, and this is a lab called STL, the Standard Telecommunications Laboratory, and that's the guy, Anthony Carpove, with whom he's working. And he joins this group as an engineer. He's working on the waveguide, simultaneously also studying for a PhD. He eventually gets his PhD in 1965. No, date of PhD 1965. Okay, all the work that he publishes for the date for which he's going to get the Nobel Prize is done by 1966. So PhD plus 1, he's almost finished with everything. So this guy Carpove, with whom he was working, he had the idea of making thin film waveguides. He said we can deposit very thin layers and use this waveguide to carry light. Kao wasn't convinced. He still thinks that fibers are the way to go. So basically what he's doing, he collected glass from various people, various glass sources, and he made many fibers, many different kinds of glass, and he was trying to see what is the problem with glass, why can't we get this thing down? Luckily for him, Carpove got a chair professorship in Australia, so he left in December 1964, and Kao became the manager of this group. He shut down on the thin film work and said, let's concentrate on fiber optics. And he made this very key observation that the losses are not due to silica. Silica itself is not giving you the loss. The loss is due to impurities which are in the silica. Okay? And then he got another guy who's a theorist. He's an engineer. He's a person called George Ockham. He was specialized in antenna theory. So with him, he sits and works out that, okay, if the losses are so much, what is the best design to have a communication network? So Kao and Ockham put together their is on this idea of how do you communicate using optical signals and fibers, and they wrote this one. They came up with this idea, and this is the famous Kao-Ockham paper. This is presented at first at an IEEE meeting in 66, eventually published. It's called Dielectric Fiber Waveguides for Surface Waveguides at Optical Frequencies. This one paper in 1966 has everything you need to know on how to make an optical fiber network. Today, you could use, in 2009, you can take this paper and pretty much design your network. This thing does everything. The choice of the mode of propagation of the fiber, dielectric loss, melting loss, radiation loss, mode stability, dispersion are examined with respect to information capacity. Physical realization is discussed, experimental investigation in optical ranges. The guy has worked out the whole details in this one paper. This is George Ockham, the theorist who worked on this. So this paper is then, it's almost it's very radical. Remember, we are at 1000 dB per kilometer, and now comes at this meeting and says, look, the problem is not silica, you can get down silica to 20 dB per kilometer. And then the magazine in the field is Laser Focus World, and Laser Focus World has a small write-up on the thing, saying that Dr. Kao observes that these experimental optical waveguides could carry 1 gigabit and equivalent to 200 TV channels or 200,000 telephone calls, despite the fact that the losses today 1000 dB, STL believes that losses of only 10 or dB per kilometer will be developed. This is the report on this. So this is kind of, it's too crazy an idea. Nobody takes it seriously. But sort of in his own words, evangelically promoting fibers. And he travels to the US, he goes to Bell Lab, nobody's interested. In fact, the only people who take him seriously are some groups in Japan, which is why today a lot of the fibers, good quality fibers, come out of labs in Japan because of the early work there. So he is not really very happy. However, one person gets to take some interest. Now in the UK, all the telecommunications like here is controlled by the British Post Office, not the Post and Telegraph Department. They are the guys who do communications. So what happens actually, there is a scientist, F.F. Roberts. He sort of pursuing his boss Jack Tillman, and won't have time for the entire story, not because of low loss. Britain and England has stormy weather, grey weather, they have lots of storms, and one day a lightning strike sort of damaged half of the network where these people were working. So they thought if we have optical fibers, it will be immune to electric damage, electrical interference from lightning, etc. That is why they were interested. Can we do it optically? That was a good reason, not this low loss business. So Tillman gives him $12 million to study this, and their initial results are very encouraging, right? And this then starts off a global race to make fibers with no loss. Eventually, the people who solve the problem are at Corning in the US. This group, most people are trying to take glass and purify it. This guy says, let's start with silica. You start with pure silica and try and make glass, add controlled dopants to change the refractive index. And in 1970, they announced optical fibers with 17 dB per kilometer. 20 dB was what he said you need. These guys have got 17 dB per kilometer at 633 red lasers. That's the only laser available at that point. And the only people in the world you could send it to at that point was the British Post Office. They sent it to the Post Office and confirmed that yes, these things have no loss. Also in 1970, you got semiconductor lasers operating continuous wave, for which the room temperature laser, for which the Nobel Prize in Physics was given in 2000. So now you have the source, now you have the fiber. Suddenly, fiber optic communication has become a reality. Kao's prediction has been sort of fulfilled. It's been, people realize that yes, he was right. And he of course leaves this lab and goes back to Hong Kong as a chair professor. He eventually becomes the vice chancellor of the university and does a lot of work for science in Hong Kong. And in the UK in those days, if you made a great discovery, you don't publish it in Nature, you go and show the Queen. So they demonstrate fiber communication to the Queen of England, and this is the successor, Ramsay's successor of Kao. And if you look at it, if a scientist would like to look at graphs, this is the graph of loss versus time, and why Kao's thing is so important. We've known glass since Egyptian periods and Venetian periods. This is a log scale in dB per kilometer. It's not progressing very much until 1966. The seminal suggestion was spurred research into this, and suddenly you have a huge drop in the loss of optical fibers. Okay. So today, optical fibers are the most transparent things that you can get. Now, what is the situation today? So that is what is figured out. Eventually, laser sources shifted not at 633, the red lasers, but today all optical communication is either around 1.3 microns, right, or 1.5 microns, where the loss of the glass is the minimum. Right? Actually, you're still dominated by the tail of some other water vapor band somewhere which you can't avoid anyway, or the SIO band. So you operate at losses, and these are much less than 1 dB per kilometer. Okay. And of course, the internet and everything is not just purely the low loss optical fiber. There have been many other developments over the years, probably which have all contributed one way or the other. Some of the key things are, of course, low loss fibers, many Japanese groups, dispersion management, which has been very, very predictive. It's not sufficient just to have low loss, right? If you send a pulse, remember you communicate in ones and zeros, which are optical pulses, the pulse spreads out. If the pulse spreads out too much, you won't be able to gather information at the other end of it. Right? So you must do something. This is called dispersion. You must do something to compensate for this and manage it. So the University of Southampton has been key to doing this. Then again, no matter how low loss it is, this let's suppose there is some loss. And if you're trying to go thousands of kilometers, probably it's not going to work. So people had repeaters. They would go over 100 kilometers, convert the signal back into an electrical thing, amplify it, and resend it down the fiber. Today, the entire process is done optically using something called an erbium lobe fiber amplifier. Again, many groups that work on it. There are many other things. The idea of that once you have optical fibers, for an electrical cable, I can't put 1 volt and 1 volt, and figure out whose signals they are. But on an optical fiber, I can communicate with green light and red light and separate them out at the other end. So we have this technique called wavelength limited multiplexing, where you use many different wavelengths of the same fiber to increase this capacity. Right? So there have been lots of scientific developments, technological development, even the whole idea of having ships which can lay out fibers across the sea. It's important. we need a lot of technology. The result of it is today we live in a world which is sort of bathed in optical fiber. There's optical fiber running, wrapping us all around the thing. And it's kind of interesting to note that in the last few years, in a way, Indian players are becoming very important. You may not realize this, but today, the number one carrier of voice traffic in the world is Tata Communications. Right? And they're probably the number one owners of capacity of submarine fiber because they bought Tyco Communications. Right? There's a company in Aurangabad called Spurred Optical. They make 12 million kilometers, 12 million kilometers of fiber every year. They're number 3 in the world. Right? So a lot of this is actually happening, here at home. Right? Nice. Okay? And if you want to know what the current sort of records are, typically these are announced at one of the